Does it work? Yes. Okay. Thank you for having me. Frank just answered the question, how far? I'm going to try to answer the question, if it's going to happen or not. So I'm going to use the present-day mass change rates from observations to put into my ice sheet model and see if you run it further into the future, what will happen to the Antarctic ice sheet in general and in the Amundsen Sea region in particular. And I'm Tim van Akker, and I work together with Bill, Gunther, and Willem-Jan and Roderick as a collaboration between the Akker and Utrecht University. So the goal is to find a committed sea level rise to the Antarctic ice sheet in its current state. However, this quickly turned into the question, what is the likely fate of Thwaites and Pine Island Glacier? Because this is, as you will soon see, the place where the interesting stuff is going to happen. So how are we going to do that? We're going to use the community ice sheet model to get Antarctica as close to present day state as we can, and then we're going to run it into the future without climate forcing. And I'll show you how. So we tune for, just as many ice sheet modelers in the room, we tune our basal friction parameterizations, we tune our ocean temperatures to get our ice sheet into a position that we wanted to have. But now we include the ACT, the mass change rates from Smith et al. In Science, into our surface mass balance rates during the initialization procedure. What we get from that is well-matching ice thickness, a very good grounding line position actually. In most of the grid cells, it's, the modeled grounding line is in the exactly same grid cell as the observations. We get well-matching ice velocities, but now we get the observed mass change rates into our ice sheet model, doing a spin-up. So we get this ones into our modeled Antarctic state. That looks like this. So if we zoom in into the Amundsen Sea region, you can see that on the left there is, or in my left, you're right, there is the mass change rates of Smith et al., but interpolated onto the community ice sheet model grid. And onto the right, you can see after we done the spin-up and we do one time step, what does our DACT pattern of our ice sheet look like? It looks like this. So they're the same. They're not exactly the same. There's small differences on the shelves. I can get to that in the break. It's technical details. So, mission succeeded. We have an Antarctic ice sheet. It looks like present day. Grounding line is in a good position. Thickness is all right. And even our DACT pattern is in there. So, we run it into the future without forcing. Well, let's see what happens. Big surprise. Thwaites Glacier and Pine Island Glacier disappear in this, or they don't really disappear, but they disintegrate in this simulation. So I ran this forward for 2,000 years. Actually, I only do, most of my runs are 1,000 years, but to make it a bit more visible. You can clearly see that, for example, the thickening in Dronning Moutland is, in my run, continuing. Also, the camp ice stream is initially also still thickening. But soon, after like a couple of 100 years, Thwaites, and then after that Pine Island, are flowing away. Now, from this result, we thought, like, what is actually happening here? Because this is the main interesting thing of this run. What is happening in the Amundsen Sea region? So this is a plot where we show 250 years, 500 years, and 750 years into the continuation, what is actually the state of the ice sheet. I can clearly see that at 500 years, so the middle plots, the grounding line, the red line, starts to move back fast. The elevation lines, which are the dotted and the striped lines, move away as well. And you can see that the inland is also starting to become red. So actually the glacier itself starts to draw ice from the inland onto the shelf. And in particular, the velocities in the Thwaites Glacier are increasing, and they're reaching about 4,000 meters per year at that point. So we really have like a massive fast collapse at this point in the run. And after 750 years, you can see that the grounding line has receded really far, that there is a huge ice shelf in front of it because we don't really have a good way to approach the calving law, so this is kind of a conservative estimate. There is no calving yet, or there is no advanced calving. And we end up with our collapsed state. So then we ask ourselves the question, is this always happening? Is this the result of the mass change rate that we introduce? And yes, it kind of is. So what you can see around here is the black dotted line is the ice volume changes on the first y-axis. Of Pine Island and Thwaites in percentage, and the sea level rise equivalent is on the other axis. And what we did is we varied a lot of physical settings, or physics in the model, and parameter settings, forcing, spin-up methods, whatsoever, whatever we could think about, to get this collapse to stop, actually. So we introduced more basal friction, different basal friction parameterizations. We played around with our, well, I named it GIA, but I don't think I'm allowed to call LRA GIA anymore now. So we varied our LRA parameterizations, our flow factor, basal melt parameterizations, and the sensitivity to that, melt at the grounding line, the resolution. We even tried different ice sheet models, and surface mass balances increases that might happen into the future. And in all of those cases, I mean, this is only a subset of the runs we did. We actually did around 60, 70 runs with different settings. They all collapse. However, it's most sensitive to basal melt. And that is the thing that can actually save us, because there is a couple of runs that I did that actually stabilize. And these are the red lines on top of this plot. Those are the lines, or in this experiments, I branched off the default run different experiments where I decreased the basal melt rates with a certain percentage, with either 25%, 50%, or 75%. And you can actually see that 50% and 25% decreases in the basal melt rates are not enough to stop the collapse. If you decrease the basal melt rates by 75%, our model basal melt rates, you can get away. The whole system stabilizes if you just do it in time. So if you do it at 400 years, you are a bit late, and if you do it at 500 years, your collapse is still happening. But if you do it before that, you can stop this thing from happening. And that's why what we're seeing around here is not really a marine ice sheet instability, because if we change the ocean forcing, our ice sheet regrows. But that's mainly because at that point there is a large ice shelf in front of it that provides a lot of buttressing onto the glaciers behind it. So that will eventually stop further retreat. So, conclusion of this experiment is that in our experiment, Thwaites and Pine Island are bound to collapse under the current mass change rates, yielding a sea level equivalent of about 1.2 meters. This is for a realistic, in our case, realistic set of parameters and forcing and physical choices of the model, spin-up states and forcing fields, ocean forcing fields. And it can be halted if you give it a significant cooling. And this cooling is, I just said 75%, which translates in our parameterization to about 1-2 degrees ocean cooling in the Amundsen Sea region. And there's a paper coming on this very soon, so stay tuned. Thanks for your attention.
Great, thanks, Tim. It looks like we've already got a couple of questions. You're gonna, nice.
Sorry, Frank. Very nice, Tim. Monday, I was kind of relieved after Petra's talk. And now the question I would like to answer is whom? Whom should I believe? The study from last week, what Petra presented in a short way on Monday, or yours? I mean, you're not that far away, as far as I understand, as a non-ice sheet modeler, because you still have these, we can stop it if we implement all these geotechnical measures, for example, curtains underneath the ice sheet and shelf. So what is your point on that? I mean, this is probably a question you expected.
Yeah, this is not a nice question, no. I saw Petra's results as well, and I really like them. That's what I want to say first. No, I mean, they're fundamentally different. Like, we include our mass change rate directly into our spin-up. Petra does a paleo spin-up, and then revolves around through present day and pushes that into the future, which is a very different approach than we are using. So I'm not saying that our method is better or that her method is better. Our method is just different, so to say. What I can say is that what I really like about this method actually is that if you look, for example, at this plot, and you look at the straight black line in the middle, that is the observations. So that is the observations of Smith et al. That are just assuming that if you don't have an ice sheet model, and you push these rates into the future, and you say, like, okay, this is going to be sea level rise at some point, that's what you get. And our results are kind of nicely grouped around this way. And actually, they say that you can actually, in the first 250 years, kind of get away without using an ice sheet model. That Antarctica is not, that the sea level rise of Antarctica isn't really, the rate is not really changing in the first couple hundred years. And that's something that I like about our results. Does that answer it? Okay.
Okay, Tim, thanks a lot. So now I can come out and say how long my run was. The run of the collapse was 100 years.
Damn.
But it was including damage, and probably there is still a lot of work to be done on that. But what in your case, I mean, what controls the yeah? Can you get it earlier, and what would be the control in your case, basal melting or something else?
Yeah, that's the short answer, basal melting.
What about calving?
There is not really a liberate calving law in Sism-Red yet. I tried, of course, to do something with like a threshold-based calving, for example. Didn't matter that much yet. It makes it a bit faster. What I would say is the most influencing these results is how you treat basal melt at the grounding line. So if you include this partial melt parameterization, the FCMP, or the no melt parameterization, for example. That was really important in these runs to consider.
All right. Do we have one more question I think we have time for.
Hi, thanks. This is a simple micropaleontologist asking a question. But in your model, obviously, it's quite logical to inhibit basal melt by cooling the waters that are close to the ice sheet. But in reality, it's also the freshening of the surface waters that can induce sea ice formation, and that prevents basal melt. So what is your take, and what can your model say about what freshening of the surface waters would do to inhibit the basal melt?
My model doesn't say anything about that. So, yeah, I've heard this train of thought that what you're referring to is basically if fresh water moves to the surface, sea ice forms, and deep water formation goes down, and therefore no warm circumpolar deep water can reach the shelf, right? I have not investigated this. If this is something significantly, what's significantly happening after a collapse, or if this also can decrease the basal melt rates. But good question.
Great, thank you, Tim. Next up, we've got our first of two invited speakers, Helene